Earthquakes cannot be prevented, but with new technologies a lot can be done to ensure that the urban infrastructure is ready when a disaster strikes. Is this bridge reliable enough to withstand an earthquake? And if it is not, can we know this in advance to prevent severe consequences? We're in Italy, where researchers are working on an answer to these questions. An earthquake's about to be simulated in the lab at the European Commission's Joint Research Centre. The strength of 2 viaduct piers will be tested. It's a typical design of many bridges built 50 years ago when adequate seismic protection was not a construction requirement.
These 2 actuators will actually simulate what would happen at the top of the pier during the earthquake motion of the ground. So they will move the pier in this direction back and forth.
Webs of sensors and high-resolution stereo cameras register deformations of the piers during the test. This data will support new methods and tools to evaluate seismic hazards for bridges across the EU.
The project we have here today aims to become a reference, an example for EU-wide action to reinforce European structures, such as bridges and viaducts, in order to better resist earthquakes.
And so the simulated earthquake begins. At first glance, we can't see much vibration, but let's play the video recording a few times faster.
A typical earthquake would last perhaps 10, 15, 20 seconds. Here in our lab, a test lasts for 3, 4, maybe even 5 hours. But this gives us the opportunity to really follow how the damage progresses throughout the whole cycle of an earthquake.
It's clear that one of the piers isolated from the bridge deck with friction pendulum bearings suffers much less damage. What happens to the rest of the bridge is digitally modelled in what scientists call online cyber-physical simulation.
We've got a computer model of a bridge that includes all its piers, including 2 piers that we're testing physically. The data we're getting allows us to collaborate the model of these 2 piers and then for the rest of the bridge.
So, would it be justified to retrofit an old bridge with seismic isolation, or is it less expensive to just fix the damage after an earthquake? The virtual model will help choose the best solution in each individual case.
First of all, with this test we have confirmed that bridges built in the 1950s and 60s are highly vulnerable in an earthquake, not as much from a security point of view, but rather economically. And secondly, we've confirmed that base isolation is an effective means of protecting the bridge and keeping it usable after an earthquake.